So continuity is one more important aspect of functions. Functions can be continuous or discontinuous, and we're going to define what it means for a function to be continuous or piecewise continuous and then discontinuous. We're going to take a look at different types of continuity. Oh, discontinuities, sorry. The main idea is it's a little bit dangerous statement, which is because it's not true all the time, but basically says that if you can draw a function in one stroke of a pen, it's a continuous, right? So if I can do like this, it's a continuous function. Well, that's true, but it doesn't really explain continuity to its fullest, because we actually have some functions that you actually have to draw by lifting the pen, and they are still continuous. Those functions are learned later in advanced calculus courses, but they exist. But you know, single stroke of a pen still describes pretty much what we are trying to look at here. So looking at, let's say, a function y equals x squared, which is the good old parabola, and y equals, let's say, 1 over x, which is the rational function. The first one will be labeled as continuous function, and the second one will be labeled as the discontinuous function. And then the second one, the 1 over x, will have the two continuous pieces. So it will be piecewise continuous, because it will have two continuous pieces where the continuity is uninterrupted anywhere other than 0. So we can pinpoint that one spot where the continuity is ruined, but as long as it's discontinuous anywhere, the whole function is globally discontinuous. So these are the ideas that we are exploring today. In order for us to define continuity, we have to first look at the continuity at the point. So we start with the first definition or theorem. Function is continuous at x equals a if, number one, f of a exists. 2, limit x goes to a of f of x exists. And 3, limit x goes to a of f of x equals f of a. Technically saying 1 is equal to 2 if they have the same value. So this is going to be the way for us to test if the function is continuous or not. So let's take a look at f of x equals x squared at x equals to 3. So when you're looking at something like this, you would go and you would say, well, the first rule is that f of 3 exists. Well, f of 3 is 3 squared, which is 9, so that exists. Then we check the limit of x squared as x goes to 3. And now you check the left limit, the right limit, they both go to 9. So it's 9 and exists. Check. 3 technically says that the number from the first and the number from the second have to be the same, and they are. 9 equals 9. So that checks. So we can claim, yes, f of x equal x squared is continuous at x equals 3. So this was the work done to show and to prove that the function is continuous at this one point. Now, how many points are there in the domain of the whole function x squared? Infinitely many, right? So infinitely many functions, infinitely many points in the domain of this function. So that means that we would have to repeat this procedure over and over and over and over again, forever and ever, to check all of the points. So it's not efficient, right? But it's good enough for us to actually spot discontinuities, which would be the next example. F of x is equal to 1 over x, and we're going to look at x equals to 0. So, number 1, f of 0 does not exist. It immediately fails there. And as soon as it fails, the function is not continuous. So you have 3 conditions that you have to remember. Function value has to exist, a limit at that point has to exist, and they have to be the same. If any one of those 3 fails, immediately you're done, right? There is no need for any further calculations. So because of this, right, because of this first failure right there, we say that f of x equal 1 over x is not continuous at x equals 0. Now observe that if you plug in number 2, it will work everywhere, because the function value would be 1/2, the limit would be 1/2, and 1/2 equals 1/2. So this function 1 over x, and you see the graph up here, function 1 over x is continuous everywhere except at 0. So globally, the function is discontinuous. But there are pieces of the function that are continuous, and you can still do calculus, you can still do mathematics, at least at those spots, on those intervals. So now the question is, how does discontinuous functions look like? Let's take a look at tax function. What's a tax function? Taxes, right? April 14th. What do we have there? We have the step function. I'm just going to, maybe I can bring up actually the tax brackets. We can create the actual graph. Tax brackets 2015, federal income tax. There we go. So let's take a look at the single. $10, $20, $30. So this is money, and that's the percent. So what it says, from 1 to approximately 9,000, so let's go 10K, 20, 30, 40, 50, 60, 70, 80, 100K. 2, 3, 4, 5, 6, 7, 8, 9, 200K. $250K and so on.
100K be to the right one?
1, 2, 3, 4, 5, 6, 7, 8, 9. Right there. All right, cool. So 1 to 9K open circle, and then 9 to approximately 37 and a half. So 20, 37 and a half, and it's 15. And then from there to 90,000 at 25. 90 to 190 at 28%. And then 33% goes above, so here we go. There's more to this graph. There's over 400,000 and then over. And text brackets are just weird. So is this function continuous or discontinuous? You will clearly say it's discontinuous. Now we would like to examine what kind of discontinuity we have. So we can call this function maybe t of x, right? So let's take a look at, let's say, this value here. This value here was for 15%. So that's at 37,450. Dollars. So let's take a look. Does the function value exist? So how about f of 37,450? If you made this much money, you are paying 25% tax. So exists. Awesome. How about the limit of the tax function as x approaches 37,450? Very good. Does not exist. This is where it fails. And the function is discontinuous. Why the limit? Why the limit doesn't exist?
So yield different values come from the left and right since it's right on the middle of it.
Excellent. So we're using the theorem from our first lecture on limits, and the theorem says if the limit from the left and the limit from the right are not the same value, the limit doesn't exist. So from the left, limit is 15. From the right, limit is 25. 15 and 25 are not the same number. Therefore, we have that limit does not exist. As soon as something fails, the whole continuity fails at that point. So we see that we have continuous pieces there, but we also see that there's this what we call jump discontinuities, because the function jumps from one value to another. Also know that each one of the line segments has the closed dot and the open dot, right? Those are the including and not including the point. Limit doesn't care about that, but f of x definitely does. So we have to be a little bit careful there. Let's just go and say function t of x is discontinuous. At 37,450. Now we can check that for every single point. We'll get the same result. Function is discontinuous at any one of those numbers. And now we're going to take a look at the continuity rules. So where do we start? Assume that functions f and g are continuous on their domains. Then the f plus g, f minus g, f times g, and then f divided by g, provided that g is not 0. We have cf and one more, the function, the exponent. Are all continuous. So n, exponent n, yes. I'm not sure why the function composition is not, maybe they have a separate thing for it.
They have a separate thing for it.
Yeah. Yeah, it is. 211. I will just add also f of g of x is continuous. Why separate this? Cool. The next part. Yes. Our multiplication by a constant. So that says that if x squared is continuous, then 5x squared is continuous. So if we add or multiply or divide or do whatever with these two continuous functions, the result will be continuous function. You know that x squared as a function is continuous. You know that x cubed is continuous. That means that x cubed minus x squared has also to be continuous. And that is by this theorem. You will use that. Actually, in Calc 2, there will be a lot of stuff to do with this. So right now we're learning the concept of it, but then use will be here and there to find continuity. And also Calc 3, it's really necessary. Now, certain problems in calculus will require you to write few sentences and solve them that way rather than actually calculating every time. Yes?
What would be a scenario that a function would fit the first two criteria where it exists and the limit exists, but f of x doesn't equal anything?
Excellent question. Let's put all three criteria down next to each other to make sure that we all see them. So I'm going to draw three graphs, and they will have slightly different functions so that we can see what it means one to fail. So 1, 2, and 3, these are the rules. And then we're just going to cross out whatever it fails. So on the first one, function value does not exist. It's a very simple one. Function value does not exist, so fa dne There is no y value for the x input that we are observing. The second one is the failed limit we just added with money. So this is where the second one fails. The function value exists. It's right here. This is your f of a. So that's cool. But we don't have the limit, so that dies. And here is the third case that the question was about. It passes the first two, but it fails the third one. So f of a is right here, and the limit is right there. And they're not the same value. So number 3 fails. So these are the three situations which can bring the discontinuity is in. And the last one is actually called the removable discontinuity because you can kind of plug this in there, and it makes it a continuous function, where over here you have nothing to plug in, and over here you can't really bend the function so that you can actually take use. So one more definition. Oh, sorry. So now definition for global continuity. Definition for global continuity. So function is globally continuous if it's continuous at every point in its domain. Function, you can call it f of x, is globally continuous if it is continuous at every point in the domain. So that's global continuity. And as I said, when you have x squared and you want to prove that that one is continuous, well, you take one point at a time and you do that forever, and there you go, right? So what we actually have, so we don't have to do that, what we have is the list of continuous functions, and then we can use that list along with the rules that we listed to come up with the overall continuity. So here it is, functions, polynomial, exponential, logarithmic, sine theta, cosine theta, phi, absolute value function, I think this should be good enough because we haven't covered hyperbolics yet. None of the other trig ones are continuous. Polynomials cover all of the infinity of the types and shapes. Yeah, I think we're good. Are all continuous? On their domains. Now this allows us to check the continuity for a following function. Absolute value sine x squared, like this, let's say. Now to solve the continuity for this problem, you get to write a paragraph. No calculate things. Remember, you don't have the luxury of computing every single point out there. So what do is you take this and you say, let's do the function decomposition. The most outer layer of everything is the absolute value function. Then the inner layer is going to be sine x, and then the most inner layer is x squared. So you see how you plug in this x squared, plug into x from sine, you get sine x squared, and then you plug the whole sine x squared for x here, and you get the absolute value of sine x squared. So that was the function decomposition where I look at the whole outside of the problem, and then I create the outer function, and then I go one step in and then one step in. You can have as many chains as you want, or as the application calls for. This is just an example. So now we start by claiming that x squared is continuous because all polynomials are continuous. So that's where you start. Then you would say that actually there is a much easier way when in this situation. You can just say all of the function above are continuous. Let's do it that way. It's much easier, faster. So all of the above functions are continuous on their domains. In this case, domain is from negative infinity to positive infinity. And function composition function composition of continuous functions is continuous. Therefore, absolute value sine x squared, absolute value closed, is globally continuous. There we go. So as you can see, we did not calculate anything in this calculus problem. We used the pre-calculus knowledge to decompose this function composition into the three basic functions. How did I do this? Well, I look first what is on the outer layer, and then I say, well, I have absolute value of something. So here is the absolute value of something. Now that something is this sine x, and then that sine was of x squared, which means x squared is there. So you can get any value, right? You get any value, and you will plug it there, and you get the value, and you plug it here. So that's if you want to compute the point. But we are not going to use the continuity at the point. There we go. We're not going to use continuity at the point for global continuity because, as I said, you have to check all infinity of points, and you don't have time for that, right? A particle there, something. So what you do is you have to learn, and this is where we finally get to the point where we'll get to talk a little bit about the exam, but most importantly, we get to talk about how to properly learn calculus and how to properly understand calculus. You saw a lot of red theorems and definitions. That is the only way to be able to get through calculus with some understanding and then hopefully build it up with Calc 2, Calc 3, and then use it as engineers. Guys, you need to know these theorems and these definitions because definition says what the concept is and theorem says how to use it. So technically it's like the steps or methods to solve a problem. So if you take a look here, I know what the continuity is, which is definition. Let's keep that aside. I'm using a lot of theorems. A theorem, first I'm using the knowledge from pre-calculus to decompose the function, and then I'm using the calculus theorems to help me solve this problem. All of the above functions are continuous because there is a theorem that says that all polynomials are continuous, the sine and cosine, the absolute value, we had that list, it was in red. So, me stating this first sentence here is displaying the knowledge that I acquired regarding continuous functions, basic functions, and whether they're continuous or not. We know the tangent is not continuous, the secant is not continuous, and so on. So now, and the function composition of the continuous functions is continuous. This is another theorem, which I wrote right under this list of functions that if you combine them, it's continuous. And here it is, absolute value function, sine and cosine function. Well, hold on, I'm looking for the, that's the one. I'm looking for the rules, which is a theorem, and here it is, also the function composition is. Now we have a triple function composition there, right? We have the function and another function and another function at the end. So let's write that. I have f of g of h. That's what we had. Where f is the absolute value x and g was the sine of x and h was x squared. So that's what we had. But it doesn't matter how many of these you chain in a row. If each individual function inside is continuous, the whole deal is continuous, which is, again, something that you are remembering. So on the exam, there must be obviously continuity question. Now, you technically have two flavors. There is a flavor where you are given the function and then you check the three conditions, set the point, right, and you say whether the function is continuous or not. And then there is this type of problems where you get the global continuity where you need to know how to get the function decomposition done in order to go through each one of these and say, yep, continuous, 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 all basic functions, and then function composition continuous, therefore, this is it. And so much important, state the rules for, let's say, that could be an exam question. State the rules for the checking the continuity at the point. State the theorem for limits, which is the left limit must be the same as the right limit, and then there is the overall limit, if they agree. So part of the test is technically free because you are supposed to just plug in the values that you plug in definition and theorems, right, that you already know. If you don't know them, well, the rest of the test might not go too well. So let's take a look at the example from the textbook. You've seen two examples done here. I just want to take a look if they have any piecewise functions for you guys to enjoy. And they don't. This page. Awesome. So problem 18. Try this one. It's a continuity at the point. So you're supposed to first figure out which point is the point in question and then try and solve it. So f of x is x squared minus 4x plus 3 divided by x minus 3. And the second function is just number 2. If x is not equal to 3 and x is equal to 3. So these are the somewhat domains. Let's see what you can do. Again, you're checking at the point. Stop. I thought it was going to be working and it would die. Turning toxic or something. So you are checking first if f of what is that point that we should be checking this at? X equals 3. Very good. So does the function value exist? Does f of 3 exist? Yeah. What is the value for it? Very good. 2. See, when x is equal to 3, f of 3 is 2. Awesome. So it passes number 1. Does the limit exist? Yeah. Yeah, it does. Because looking at this one, well, what does it?
I thought it did because I factored the top to x minus 2.
X minus 1?
X minus 1, yeah.
And then it becomes 1 over x minus 1, right?
So it would be x minus 1 over 1, right?
X minus 1, yeah. X minus 1 over, yeah. So x minus 1, so that's 3 minus 1, so 2. So 2 from both sides, right? So cool. So that works. And then we have 2 from the first and 2 from the second. So the third one works. So yeah, everything works. Let's write it out. So the answer is yes. This function is continuous. Even though it's a piecewise function, it is continuous at 3. But let's write that down. So the first thing is, how's the f of 3? F of 3 is equal to 2. So now number 2. Remember, the limit is going to look at every value around the point that you are looking at. So it says you need to find the limit as x goes to 3. Well, we factor out the top x minus 3, x minus 1. The bottom is x minus 3. These guys cancel. And all you get is number 2. So this one check, and then 2 is equal to 2, check. So yes, f of x is continuous at x equals to 3. Perfectly continuous. It really doesn't matter what kind of function you have, as long as you are able to compute it, as long as you are able to check the limit. And then if the values are the same, you're good to go. If the values are not the same, then you'll have to say it does not exist at that point. Again, which brings me to the point to say that you need to make sure that even discontinuous functions are continuous somewhere on their domains. And then we can at least use that for our problems. So we have now the continuity at the endpoints and continuity on the interval. This is mimicking exactly what we did so far. Continuity at the endpoint means that limits exist. So, but these are the one-sided limits. So let's say continuity at the point. And we take a look at, well, first, continuity at the point, all the same. Sorry, at the end point. End point. Hang on, guys, I started getting confused. All right, so here is some unknown function f of x goes from, let's put it on the xy grid because we can. So starts at A and ends at, let's say, B. So this is the line segment. Maybe this line will continue forever. We don't know. We don't care. We just want to check what's happening from A to B. So continuity at the endpoints, you know that the piece inside is continuous. You can see that, but the question is what's happening at the endpoints. Since these are the values on x-axis as input, you will use only one-sided limit to pretty much do the same procedure we have been doing so far. So instead of writing, see in this case over here, I wrote x approaches to 3. Now it's going to be x approaches 3 minus or x approaches 3 plus because that's the left or right approach. But we know that as long as both of those left and right approaches are giving us the same value, the overall limit exists. But now those type of limits, the one-sided limits, are it for the whole thing. So we are technically redefining this into number one, f of a exists. Number two, any of the, well, no, not any, the appropriate one-sided limit. So let's just put limit x approaches a, and I'll put plus minus there, of f of x exists. And then for number 3, 1 should be the same as 2. So whatever number you get should be the same. Questions? Concerns? It's more interesting that I get to be more effective and far more clear in calculus classes than in algebra class. Right? Or you just don't know yet what to ask. It's like, what the hell is going on? Is there more of that? So we're talking about continuity. Right? We are at RBCC, we are right, 3rd floor, if you're lost. And we're talking about continuity. And we defined that you need to know those 3 rules to find the continuity at the point. And then there was a separate theorem that said that each one of the individual functions, which are continuous and which are not. And then there's a separate theorem that says that combinations of functions or function composition of continuous functions ends up being continuous as well. So those are all the theorems. You can call upon them. And as I said, you saw earlier, some of the problems that you're doing in the calculus now is going to be writing a paragraph rather than computing things. So we just wrote a paragraph in this case to solve the problem. That concludes 2.6 And we'll talk more about this stuff later.